This webinar will highlight the true potential of remote aerial imaging and the industries that can benefit from it, and how FLIR thermal imaging sensors collected and analyzed with measures, processing, and analysis tools are leading to the use of drones into the next frontier. To talk on the topic, we have with us Brett Kanda. Brett manages global sales for FLIR's SUS business and has been deeply integrated in the commercial drone industry since 2013. Brett co-founded two separate drone companies focused on remote sensing and actionable data. Previously, he has worked for the Nevada Institute for Autonomous Systems and the FAA-designated Nevada's UAS test site as the Director of Business Development. At NIAS, Brett worked with the FAA policymakers, private industries, and academia to help progress the FAA's mission to safely integrate UAS into the NAS. Our second speaker is Ben Brautigam. Ben is the head of design at Measure, the leading aerial intelligence company enabling enterprises to realize the transformative benefit of drone technology. Previously, Ben co-founded AirNest, a Pennsylvania-based startup designing flight planning and analytics software for unmanned systems. Ben is the second UX designer and TEDx speaker on design and autonomous systems. Our third speaker is Ilya Rosenfeld. Ilya is Measure's head of geospatial architecture and is a champion for applying open geospatial standards to drone data. Ilya's interest in geospatial technologies and geoscience dates back to his work with FAA and USDA almost 20 years ago. Over the past decade, he helped several startups and corporate innovation initiatives get off the ground at companies including Boundless Spatial and NetJets, helping them make Go Geo part of their DNA. Now I would request speakers to take over the webinar.
Maha, thank you so much, and thank you for having me, and good morning, good afternoon, good evening, depending on where you are in the world, as I know we have a global audience today, and most of you are likely going to be in your homes. So before we get started, myself, along with the entire FLIR family, want to send our best wishes to all of you who are tuning in, our customers, partners, friends, families, and everybody who's doing their best to get through these difficult times. So please stay healthy, and we appreciate you taking the time to learn a little bit more about drone-based thermal imaging and GIS with us. So for the listeners who are not familiar with FLIR, we are the world's leader in thermal imaging and intelligent sensing solutions. The company was founded in 1978, went public in 1993, and has approximately 5,000 employees across the globe. The company is headquartered in Wilsonville, Oregon, as well as Arlington, Virginia, and the company is broken down into two main lines of business: the Government and Defense Business Unit and the Industrial Business Unit. So for the purposes of this webinar, we're going to be discussing the capabilities and features of our long-wave infrared commercial drone payloads. Our SUAS business offers both plug-and-play integrated thermal camera payloads in partnership with DJI, as well as drone-agnostic payloads for people who are flying anything other than DJI. So during today's webinar, we're going to be reviewing the following topics: the basics of thermography and thermal imaging. We're going to be discussing the importance of resolution, the difference between qualitative and quantitative analysis, the benefits of electro-optical infrared imaging, or EO/IR, and then some best practices around thermal mapping. So what do we do at FLIR? Our sensors, through non-contact techniques, are able to sense the infrared band of the electromagnetic spectrum. What our eyes see is the visible light spectrum: reds, greens, and blues. So what that allows our technology to do is to see in total darkness, see through obscurance such as smoke and fog, measure temperature in every pixel within the image. We can do enhanced long-range imaging, and we can accurately detect people and animals with AI and machine vision algorithms. So thermography is the science behind what we do. And one of the biggest misconceptions of thermal imaging is that it's the same thing as night vision, and it's absolutely not the same thing as night vision. Night vision takes a small amount of visible light and amplifies it, while thermal imaging is detecting emitted heat and is totally unaffected by light sources. So see, these are some of the main concepts of thermography: emissivity, radiometry, MSX, and frame rate, resolution, and lens are all variables that are going to affect how you capture your data. I'm going to be getting into each one of these in detail here in just a second. Emissivity. Emissivity is the ratio of energy emitted by an object compared to the energy emitted by a black body. More easily put, every single thing in our environment has a different composition, chemistry, shape, from the ground that you're standing on to your skin to the computer that you're looking at. Everything interacts with infrared radiation in a different way. So it absorbs and reflects infrared radiation at a different rate. And therefore, we have known values to calculate emissivity. So the general rule of thumb is that the higher the emissivity value, the more reliable the temperature data. The lower the emissivity value, the more difficult it is to retain accurate temperature data. So you'll see something like a polished aluminum that has an emissivity value of 0.04 to 0.06 versus something like wet soil, which has an emissivity of 0.95. Now, if you want to become a certified thermographer, there's techniques that you can learn to actually measure emissivity. But for most operators, it's easiest to just go off of a chart. So this is something that's going to be really important as we move forward, because drone operators within their frame are going to have a ton of different objects. The luxury of a handheld camera or a fixed camera is that you can manage from closer distances what's going to be inside the frame of your image. Emissivity is also the most important factor for temperature accuracy, which will be more relevant when we start discussing qualitative versus quantitative analysis. Field of view. Our commercial drone payloads come in 4 different lens sizes, 9, 13, 19, and 25 millimeters. They also come in 2 different resolution options, a 336 by 256 and a 640 by 512, which is considered the highest resolution that we offer in drone payloads. Generally speaking, the 9 and 13 millimeter wide field of view is going to be preferred by public safety operators, firefighters, search and rescue, and the 19 and 25 millimeter options are going to be used by industrial inspection users. So to get a little bit more into resolution, so for those of you that are drone operators tuning in, some of you might be flying the DJI Mavic Enterprise Dual or the Parrot Anafi. And the thermal sensor that's inside of those payloads is what we call Lepton. Lepton's a low resolution microprocessor, which has a resolution of 160 by 120. For users that are taking images with the Zenmuse XT2, you have a higher resolution camera that's based on our Tau 2 core. Now the high resolution on that's going to be 640 by 512. So what we're going to be showing in this image here is what we call spot size ratio. So the circle that you're seeing in the middle of your screen is an 18-inch in diameter heated up pizza pan that is sitting on concrete. Image on the left is taken with Lepton. Image on the right is taken with a high resolution XT2. This initial image is taken at 25 feet, so not a huge difference, but you can definitely see the outlines in the concrete. As we move a little bit higher to 50 feet, you'll start to see a little bit less definition on the left and more definition on the right. Now, when we get to 100 feet, it's almost impossible to make out that pizza pan on the left, and you're maintaining resolution on the right. So here's a graphical representation of spot size ratio. X-axis here is going to be your flight altitude in AGL, which is above ground level. Y-axis is going to be the size of each pixel, or basically the size of the target on the ground. So if you're using a high resolution camera, you can fly higher and still get pixels on target of something that's smaller on the ground. If you're flying a low resolution camera, the higher you fly, the bigger the object on the ground is going to have to be for you to see it. Okay, an important concept to understand for thermal mapping in GIS, qualitative versus quantitative analysis. For qualitative analysis, you are not concerned with the temperature values embedded in every pixel. You are more concerned about something being hot in one area versus in another. A good example of qualitative analysis is going to be firefighting, search and rescue missions, some types of roof inspections, and ultimately you're just going to be doing a high-level analysis of your asset or whatever your target object may be. Now, quantitative analysis means that you are relying on temperature values within every pixel. Some good examples of this are industrial inspections, cell towers, electrical panels, solar panels. You are going to be taking a baseline measurement of temperature values to baseline against your operating parameters of your asset. So we will touch a little bit more on this when it comes to mapping and some of the limitations of quantitative analysis when doing point cloud or orthomosaic generation. So most of our SUAS payloads have dual capabilities, meaning they have a 12 megapixel RGB camera alongside a high resolution thermal camera. So FLIR MSX is a patented technology that basically blends the two images together. As you can see here, the image on the left has MSX turned off, so you can only see the temperature differentials on this vending machine. Image on the right has MSX turned on, so you now get the outline of the RGB image in your thermal image. It's really useful for applications like this. Asset inspection, where you need to see the label or tag on whatever your asset may be. Image on the left without MSX, image on the right with MSX, where you can see the label and that it's a propane tank. And the camera on the left is an example of the Zenmuse XT2, which is our high resolution, high powered camera. So some of the common use cases for our UAS technology are public safety, fire departments, police departments, search and rescue and tactical operations, as well as security and infrastructure inspection. These are the main use cases that we've seen, although we hear every day from very creative users that are finding new ways to utilize our technology in the field. But these are the main use cases that we see. So traditionally, thermal users have used our in-house software, FLIR Thermal Studio and FLIR Tools Plus. Now, FLIR Thermal Studio and Tools Plus both give you the ability to what we call thermal tune your image. So you can change the color palette, you can set temperature ranges, you can do a number of different things to make sure that your thermal image is optimized. Now, when it comes to creating 3D models and point cloud generation and orthomosaics, we fall a little bit short, and it's a very new science to want to do that, although we are hearing that the demand is growing every single day. Hence why we are starting to initiate relationships with companies like Measure that are moving at a fast pace in the drone industry and are starting to create thermal data sets with GIS applications. Now, there are some limitations when it comes to creating 3D models with thermal data. Some of them are listed here. But when you are doing point cloud generation and orthomosaic generation, the rule of thumb is that you only want to do qualitative analysis. And the reason you want to stay away from quantitative analysis is that concepts and physical attributes such as emissivity, T-reflect, distance, humidity, ambient temperature, spot size ratio, and wind speed are not being currently calculated into the algorithm when processing that imagery. Without those considerations, it's going to be very, very difficult to get an accurate temperature reading. Generally speaking, it's better to fly lower and slower as you're doing your mapping mission, and also to have a high overlap and side lap, at least 80 by 80. Now, the best time of day to fly depends on your use case, but the general rule of thumb is that you want to fly when delta T is the greatest, which is solar loading. How much infrared radiation has your target taken in throughout the day? So if you're doing solar panel inspection, you're going to want to fly at high noon. If you're doing a roof inspection, you're going to want to fly about 30 minutes after dusk. And again, it really depends on the use case on which time of day you want to fly. So for some more resources around our SUAS business, you can check out the FLIR Delta page. There's podcasts, webinars, videos, and more info on everything that I've just covered. If you're interested in taking it to the next level and becoming a certified thermographer, the Infrared Training Center is a wholly owned subsidiary of FLIR. Infraredtraining.com has all of the course sites and the different options. We do offer training courses around the world. Our YouTube page also has some great videos and resources for learning. So over to the Measure team.
Thanks, Brett. And hello, everyone. Thank you for joining. And Brett's, those best practices are really an ideal segue as we move into discussing drone operations and the mission process end to end from capture to analysis. At Measure, we've leveraged our experience as a commercial drone operator, inspecting thousands of global assets to design and build streamlined software that consolidate all the parts and pieces of drone operations into one place, and that is ground control. Ground control consists of three main parts. The first of which is a native flight application for DJI aircraft, where operators can manage missions, check airspace, fly manually, as well as execute automated grid and waypoint missions. Using captured imagery from the app, Ground Control's web platform then offers mapping and data analysis tools powered by Pix4D. And then layered on top of that is program management, where program managers can plan missions, track activity, manage personnel, equipment, and other resources. The first step in the mission process is planning and program management. So our web platform offers web-based grid planning, as seen in this example here, as well as layers in mission scheduling, resource management, flight logging, and program reporting. And once imagery is captured in the field, the web platform can be leveraged to process that data into orthomosaics, DSMs, and contour maps, in addition to the IR product work we have in progress now. And to start that flow, once an operator or an analyst uploads imagery into Ground Control, they can view images on a map for review and have the ability to exclude individuals from being processed. And once validated, the project is then sent for processing with a few clicks. Pix4D will then return the completed mission data products back into Ground Control, where they can be viewed in our own mapping system. Features here include export to GeoTIFF and GeoJSON, measurement tools including distance and area. And since this all lives inside the Ground Control ecosystem, you can also access toggles to other layers of your program, such as flight logs, flight plans, site locations, and more. Coming soon, we're working on support for thermal mosaic layers, ground control points, as well as map annotations and sharing. Feel free to check out measure.com for more on this and to start a trial. So right now, I'll pass back to Ilya to discuss GIS applications.
Thank you, Ben. GIS is all about the kinds of questions we can answer with the help of spatially enabled data. We apply descriptive and predictive techniques to answer these questions. We can answer simple questions, like simply solving for a location of an event or a thermal anomaly, let's say. GIS is also a modeling tool that can treat thermal data as a standard input to answer more complex questions. So here we have some use cases and questions we can ask, sort of ranging from simple to more complex, that involve deeper integration with other models. A simple question may be something like, where is a thermal anomaly located? You can visually identify that on a map. A more involved question is which components are affected by this anomaly. Where might be underground leaks? A more complex modeling question would be, is in an emergency situation, what is the best way to access that area or that component in a real world setting? And finally, yet a more complex question we typically answer with GIS is, over time, which components may be likely affected again. And in a situation where remediation has been applied, that is, we've already identified some anomaly in the past, has that remediation actually had effect over time? In case of solar energy, it's fairly typical to identify where outages are located, which solar panels are affected. With some more analysis and overlay analysis, we can identify which infrastructure assets are actually affected by these anomalies. And finally, we can apply spatial aggregation techniques to quantify the actual effect, aerial effect of these anomalies. So we can identify just how much power is out, or how much area is affected, or how much of roof area is affected by a specific type of stress. In agriculture, a typical question to ask is, how much impact does this thermal signature actually have on predicted yield, and so on. So as you can see, there's a breadth of questions we can answer with GIS. So how does this work? In GIS, we're used to a pretty sort of common framework where we deal with thematic georeference data organized as a set of raster vector layers. We access attribute data and perform various computations and simulations on top of this. So the entirety of geoprocessing and spatial analysis body of knowledge is applicable to thermal data with limitations, obviously. We need to be smart about how we're using the data, and I'll get into it in just a second. And we can deal with thermal data pretty much in any GIS environment, on desktop, in cloud environments, and so on. In measured ground control, georeferenced thermal mosaics are represented as GeoTIFF files. So we're all familiar. It's a standard kind of open format, and where raw values are codified directly into the grid. So we're really just dealing with gridded data fundamentally. It's a georeferenced raster layer. It's important to note that the gridded data values in the actual raster layers are going to be represented in sensors units. So we need to be very careful about what those actually mean and then how to process these. But nevertheless, the sensor readings are accessible directly from the GeoTIFF. Resolution is a function of sensor resolution, flight altitude, and camera optics that Brett talked about earlier. And finally, accuracy is also as a function of planning, ground control points, and other control techniques we can apply for quality control. So everything here really is just another standard photogrammetry problem to some extent. So in this example, if you focus on the image in the lower right, you'll see that this pixel we're zooming in on here in the GIS environment, QGIS in this case, we can see that there's two bands actually underneath this pixel, or rather there's two values that we can query directly. In band 1, we actually see the sensors reading. And as I mentioned before, we need to have rigor about how we actually process that value. It does not necessarily mean that this is temperature, but we can apply various models and functions to actually interpret that in GIS using techniques like raster algebra and more sophisticated techniques. And the second band, in this case, represents what we call a data product for visualization, and that is a grayscale value that specifically has been pre-processed in order to produce a visualization. So this is sort of the gist of it. So turning a little bit to a specific example. So let's take a use case where we can actually use a combination of thermal data, visual inspection, and the fact that each image actually has a location geotag in it to determine approximate location of an anomaly. So simply by scrolling or through examining individual images captured by a drone and knowing the location of the image taken and interpreting the heat signature by looking at hotspots, cold spots, or normal modes, we can identify the rough locations of that event. And that is a really simple way of using a combination of thermal data, location, and some sort of infrastructure overview. Next up is a more sophisticated example. We can actually compute specific items that are affected by an anomaly. So imagine that the picture on the left is actually an overlay that is directly georeferenced over infrastructure schematics. It could be schematics, it could be vector data, it could be simply a PDF file that, as shown in this case, you see a PDF file that simply shows a layout of solar power plant, as well as vector features of the individual panels that are affected. What we can do is we can apply raster analysis to query specific values out of the thermal raster layer. And by finding a location and then applying overlay analysis, we can find the specific features that are affected. And from there, the sky's the limit, because if the actual underlying infrastructure layer has enough rich attribute information, that we can do various things like identify specific part numbers. We can aggregate the effects, even doing things like aggregating cost of replacement and so on. So very rich possibilities where thermal data that's georeferenced begins to interact with other layers that represent infrastructure and data about that infrastructure. Lastly, I'll mention this is thermal data represented as a raster layer becomes an input really in any GIS environment we're familiar with. The slide it's an overview of commonly known frameworks out there and software products. This is not trying to be exhaustive here, but generally speaking, if you think about what happens in Esri desktop software, you can take something like the raster analysis toolbox, for example, and begin to, first of all, analyze raster imagery, including thermal data, and you can model anything you want really on top of this and create geoprocessing routines and whatever else is required, visualization. More or less the same thing we could do with QGIS, a free and open source tool out there, my favorite, and so on. So in the web mapping world, we build web applications that display raster data and vector data. Typically, you see this manifest in various web mapping products, Slippy Maps, and what have you. And both Mapbox and OpenLayers are very robust frameworks for doing that. So, standard techniques like tiling raster layers and so on really are applicable to thermal layers, just the same as they would be to RGB layers that we're familiar seeing in the orthomosaics, for example. So it's really more or less the same problem, as long as we keep an eye on the interpretation aspect of this, because obviously thermal data it's not in the visible range. We need to be careful about how we visualize it and so on. So I think it's possible to be very creative here. Lastly, I'll mention GeoServer, MapServer. These are your server side or cloud side, as they say now, I guess. Frameworks primarily used for disseminating spatial data. Again, thermal data is another raster layer. So it's possible to take that layer and actually disseminate it through standard web services like OGC web services, allowing for client GIS software to just connect to these services and consume thermal data that way. And lastly, GDAL, very robust framework for geoprocessing that is increasingly being used to build very sophisticated cloud-based processing systems. Virtually everyone in the last few years, I think, has found a way to actually use these in the cloud. And again, it's a raster data set, so we can actually use the same exact techniques we've been using for other type of raster data with GDAL and create very robust processing pipelines. And I think that's that. Back to you, Brett.
Thanks, Ilya. And I guess that will move us right into the Q&A section. Julie, what's our first question?
Thank you, Ben, Brett, and Ilya for your very insightful presentation. Now we'll move for the Q&A. Our first question is from Dave, and he wants to know how quickly one can produce drone to map data services such as feature or web map tiles.
I'm gonna try to tackle this. Could you please repeat the question? Would you mind?
How quickly one can produce drone to map data services such as feature or web map tiles?
Sure. So the process, the overall process generally, and I guess I'll take that. The process is to upload the source data into ground control, and then kick off the processing, depending on the number of input images and other parameters. It may take something, anywhere from half an hour to a couple of hours, let's just say. Really, it's a function of the size of the job. But once that happens, at least in ground control, and once the data product is actually generated, let's assume you're creating an orthomosaic or an IR layer. Once that's created, we have a system that progressively tiles the output, which means that when you're on our system, depending on which part of the map you're examining, will be tiled in real time. And so it's all kind of happening in real time, I would say. If there's any interest in consuming external tile service out of this, I would like to know, and we certainly have a capability for doing so. The process would work roughly the same. It takes about some amount of minutes, some number of minutes, an hour, a couple maybe, to generate the actual source data product, and after that, the tile services are the tiles are automatically created.
So we are moving toward the next question, and Aman wants to know which is the best measure to produce the map for underground water utilities like supply line and sewage line.
I'll touch that from the thermal perspective and then hand it over to Ben and Ilya about mapping it. But one of the misconceptions can be underground leakage issues because thermal imaging and long wave infrared cameras cannot penetrate the surface. So if there is a leak or something happening below the surface that is affecting the ground temperature, we would be able to see that. But it really depends on how much liquid is being distributed amongst the area. So again, we cannot see underground for water utilities like supply line and sewage lines. Something would have to be happening on the surface. But that's how thermal imaging works in that type of use case.
Okay. So our next question is from Alessandro, and he wants to know how can this technology be used in highways?
Highways. Thermal imaging, I would say, has there's less value in thermal imaging for doing highway reconstruction, but there is a ton of value in mapping highways. So Ben and Ilya, I guess you guys can take that from more of an RGB perspective versus thermal.
Certainly. So I would also defer. I'd have to think about the applications in thermal orthomosaic in this case. I'm simply not familiar with the space enough to comment on that. But in the ortho space, obviously, a drone allows you to capture very high resolution imagery. That's first and foremost. This is something you can never accomplish with standard satellite data. We can capture imagery to centimeter or 2 centimeter resolution. I think if there's value in that sort of resolution of a specific highway segment or construction site and so on, then there's clear application of that. And furthermore, I'll say this, we also produce elevation models as well, right, on the contour maps. So that could be another dimension that could be of interest for highway, either design or management. I'm not sure exactly what the use case is, but fundamentally, I think that's the application space.
So next question is from Glory, and the question is, what open source software can you recommend for processing drone data?
Yeah.
Over to you.
Sure. It really depends what we're talking about, but I'll just assume that we're talking about imagery. There are quite a few frameworks available for different problems. This is something we think about day in and day out on the engineering team at Measure. We find a slew of tools available, very valuable, including GDAL. So I'll just do a shout out for GDAL. I think it's a really valuable tool for orchestrating processing, quality control, and so on. And we make huge use, I would say, of desktop tools like QGIS. I could go on for a while on this. Whoever asked the question, feel free to reach out to me and we can have a conversation on that topic. It's a favorite topic of mine with my experience in open source geospatial technology.
Great. The next question is from Manish, and the question is how this will be used for crop identification, health mapping, soil health, and what more for agriculture?
Yeah, that's a good question. So the main value of thermal imaging for agriculture is being able to see irrigation runoffs and moisture levels within your farm. Now, the majority of the time when I get inquiries for agriculture, I tend to push the user towards multispectral imaging, which will be able to diagnose crop health and things like that. The bands that we're working in for long wave infrared imaging is not going to give you that level of data. So really thermal imaging is just going to be used to measure moisture and see the runoffs within your area. So multispectral is probably going to be the best camera to use for getting any type of health data and things like that.
Next question is from Rafael, and his question is, does this software process in the cloud?
Yes, the answer is positive.
And he also wants to know that, do you have training in Brazil?
I'm sorry, do we have what?
Infrared training center classes?
Yeah.
I would assume. Yes, we do. Infraredtraining.com has all of the an up-to-date course list and class list.
Next question is from Mutsiadin, and the question is, he has been working with the DJI Mavic 2 Enterprise Dual, which can't produce a radiometric thermal image, just a JPG of visualized thermal image. Is there any way to derive radiometric information from data like that?
Yeah, it's a great question. So when you're in the field and you're operating an enterprise dual, and again, earlier in the presentation, I mentioned that it's the lepton core that is inside of the enterprise dual. And because the resolution of that camera or core is 160 by 120, you're able to do spot meter and real-time temperature values. But when it comes to exporting our JPEGs, you're not able to do that because of the lack of pixels within that image. But generally speaking, if you want to do radiometric analysis, the more pixels, the better. And with something that is 160 by 120, it's going to be difficult to get accurate temperature values. So unfortunately, you're only going to be able to get temperature data in real time while you're flying, as opposed to being able to export our JPEGs.
Perfect. Next question is from Jess, and the question is, would you use more of qualitative or a quantitative approach to measuring groundwater input into streams using UAS IR imaging?
That's a good question. The majority of users, for drone users at least, are doing qualitative analysis. Unless you are a certified thermographer, it's going to be very difficult to understand how to get to a, let's say, plus or minus 2 degree temperature value. So in that type of use case, I would stick to qualitative analysis, although water has a fairly high emissivity value. So if you are a thermographer, you would be able to compensate for all the environmental factors to be able to get an accurate reading. But if you're not a thermographer, I would stick to the qualitative analysis.
I'll add to that quickly is even if you're using qualitative analysis to interpret the heat signatures or the thermal signatures in the thermal layer, and feel fairly confident that the anomaly you're looking at or specific event of interest you're looking at, something you want to investigate, then you can obviously use hydrological models in GIS to then compute various other aspects having to do with flow, whether it's a source of flow, consequences, and various things like that.
Our next question is from Tobias, and the question is, can FLIR comment on what use cases would suit for MWIR more than LWIR?
Sure. Yeah, so mid-wave infrared is generally going to be between 3 and 5 microns in the wavelength range. So it's going to be good at detecting gas leaks and carbons, whereas long-wave infrared is going to be between 8 and 14 microns and much better for temperature measurement. So when you see our OGI, which is optical gas imaging cameras, most of those are going to be mid-wave thermal cores, and then payloads like we've been discussing are going to be long wave for temperature measurement and night operations.
Perfect. The next question is from Ephraim, and the question is, what might be the main cause for loss of control between drone and control?
Yeah, I'll tackle this one. Certainly, safety is the #1 priority when doing any field operations, and the drone, at least for DJI aircraft, at the hardware level, does have certain fail safes at available to operators, such as stopping the drone, stopping the automated flight, doing return to home if necessary, provided there's a GPS point for the drone to return home to, but always obviously sticking to standard operating procedures and regulatory guidelines as well.
The question is from Ephraim as well. If he has to conduct agriculture mapping, crop health mapping, what time is suitable?
That is a very good question. I don't have a good answer on that, to be honest. Ben, Ilya, do you guys have a good idea when the best time to fly is?
I don't have an answer right offhand, but I have a way to get one. So if whoever's asking a question, feel free to reach out directly, and I'm actually get that answer for you.
Yeah, same here. If there's anything we don't answer, we can follow up after the webinar.
Absolutely.
Sure. The next question is from Vijay Kumar, and the question is, can we find out net radiation by using this?
Net radiation? No.
Yeah.
No, you cannot.
The next question is from Glory, and the question is, can the trainers... Oh, okay. So she actually wants email addresses of the presenters. Of course, Glory, you can get email addresses of the presenters, and you can ask them any questions after the webinar. So thank you, everybody. Thank you for joining the webinar. I appreciate attendees for sending us such an insightful questions. And I am very thankful to the presenters for giving an insight on drone thermal imaging.